Hello and welcome back. In example 3, we're asked to find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Now you may not be used to this kind of parabola. This is a x equals y squared type parabola instead of a y equals x squared type parabola. So this is a right-left opening parabola. And in this case, because we have, if we solve for x, we have x equals y squared over 2. That's going to be a right opening parabola. Let's start drawing a picture for our first step. Okay. If we want, we can plot a few points. Like if we have y equals 0, you're going to have x equals 0. That corresponds with this point, 0, 0. If you have y equals 1, you're going to have x equals a half. So, I don't really want to draw x equals a half. If you have y equals 2, you'll have 2 squared, which is 4, and then that divided by 2 is x equals 2. So y equals 2, x equals 2 corresponds with a point on the graph. Now we know that this is going to be a left-right opening parabola because, again, x equals y squared. This kind of a form. So the parabola is going to open up to the right. We're just drawing a sketch of this parabola. Now the problem asks, find the point on this parabola that is closest to the point 1, 4. 1, 4 is right here. Now we could estimate that. We could say, well, maybe it's right around, maybe it's like 2, 2, something around there. That looks like a pretty close point, because as you go to the right, the points get farther away. The points in the parabola get farther away from 1, 4. And as you travel this way along the parabola, the points get farther away as well. So it's going to be somewhere around here. But let's draw a picture of just 1, 4 to any arbitrary point on the parabola. I'm just going to pick another point in the parabola, let's say right here. And we're going to think about the distance between those 2 points, between 1, 4 and x, y, where x, y is any point in the parabola. Let's call that distance z, because we already used up x and y. Now the second step of solving these optimization problems is to come up with some kind of function that models the thing that you're trying to minimize. Now if we look at the closest to the point 1, 4, that means minimize the distance between those 2 points, between the parabola and point on the parabola and the point 1, 4. Now that distance, we can write this distance. We can write it as using the distance formula. We can write z equals the square root of the difference of the x's squared and then plus the difference of the y squared. Or you can think the Pythagorean theorem. You can make a little triangle, and the sides of the triangle, the legs of the triangle, you can figure out they're going to be x minus 1 and like 4 minus y or y minus 4, depending on how you make the triangle. And then you could write the leg squared plus the leg squared equals the hypotenuse z squared. But the distance formula is just another rewritten version of the Pythagorean theorem. So let's use the distance formula because we're talking about distances. So here we have it, z, which is the distance between those points, written as a function of x and y. Now I didn't write the x, y here because when we look at this, if we're going to take the derivative later of this distance function, it's kind of painful because we have this square root. Taking the derivative when we have a square root is a little bit difficult. Let's instead think of, instead of the distance between these 2 points, let's instead think of the square of the distances between these points. So if we square both sides, we get a different kind of function that has different values, but if we minimize the square of the distance between those points, then we'll have minimized the distance between the 2 points. So that's the key thing that we're going to use here to help us save us some work. So I'll say that again. So if we want to minimize the distance between 2 points, we can instead minimize the square of the distance between those 2 points. And it'll be at the same place. Either the x the same x comma y point. So like imagine if the distance between 1 comma 4 and the closest point, let's say that's 2, well then the square of that would be 4. Any other point, if that has a longer distance to 1 comma 4, then the square of it is going to be bigger than 2 squared. It's going to be bigger than 4. So by minimizing the square of the distance, we're actually going to minimize the distance itself. Now this is a much easier function to work with. We'll call this f. And as long as we're changing f, do some work off to the side. As long as we're changing f, let's try to change some of these, get the variables all together into just one variable, is what I mean. Now here it's easier to solve for x in terms of y. So we have x equals y squared over 2. We're going to replace out this x here with y squared over 2. So we're going to get the square of the distance function as a function of y only. So again, this is not giving us the distance between the 2 points, between 1 comma 4 and a point in the parabola. It's giving you the square of the distance between those 2 points. That's okay, as long as we minimize this function, we'll have minimized the distance function. And this is, again, much easier to work with. At this point, we've done number 3. So now we're on to number 4, which is finding the max, or min in this case, minimize the distance. So to do that, we need to get the first derivative. It's going to involve a chain rule. The derivative of the inside is going to be 2y over 2, which is y, and then the derivative of -1 is 0. And we have plus, by a chain rule, 2 times y minus 4 times 1. You don't have to write the times 1 again, I'm just doing it for emphasis. So now we can distribute the 2, distribute the y. We'll get y cubed minus 2y plus 2y minus 8. So y cubed minus 8. As a next step, we're going to figure out where the first derivative is 0 and where it doesn't exist. Well, the first derivative is 0 when y is equal to 2. And then the D and E case doesn't happen because this is a polynomial. So we did that off to the side. Now we can find, so that's the y value then that minimizes the distance. Now we can find the corresponding x value. I mean, it's actually in our picture, a y value of 2 corresponds with an x value of 2. But in case you didn't have it, you can find it by using the relationship that we set up between x and y, which was actually given to us. This xy point on the parabola satisfies this equation. So this is the equation that relates x and y. So we can so that's the one that satisfies that equation. So we have x equals 2 squared over 2, which is 2. So the point 2, 2 is actually the point that on the parabola that's closest to the point 1, 4. Thanks for watching, and see you next time.